So now with unit 4, right? We're talking about forces in 2 dimensions, right? So that's what we really need, that vector components part that we just covered in unit 3 and applying it to forces. So our end goal, right? We want to be able to solve a problem like this, right? And this problem is special because this is a problem where we really focus on the concept of equilibrium, right? So how do we put things to where like they stay where they are? Like, and understanding how we can get those forces to be balanced, right? So with that type of equilibrium problem, right? Suppose that a student pulls with 2 large forces in order to lift a 1 kilogram book by 2 cables. If the cables make a 1 degree angle with the horizontal, then what is the cable tension in the cable? So we got talking about different forces here, holding them in different angles, and we were talking about equilibrium. So at the end of this, we want to be able to make sure that we can solve this type of problem. So let's take our small steps to get to that, right? And like I said, this unit shouldn't take too long. Look at the units, the sections that we have. We only have 5 sections, right? So another angle on adding another angle to force equals mass times acceleration. Adding and resolving forces, right? Using vector components to analyze equilibrium state situations. That's where we're going to really get into like the main part of this unit. And then using vector components to analyze acceleration along surfaces. These and the inclined plane analysis. These last two are going to be like special cases, especially talking about what comes to friction, right? So like these two, I'll spend a little bit of time on, but not too much time. But we'll go through it. But it's really going to be focusing on these first 3 right here. So let's try and cover the most of these 3 today. And like I said today, normal class, we're going to end at about 8:30. So as we go through these, right? Let's just start with off with kind of like a little bit of review, right? So remember we had these and we have our free body diagrams. So let's take a couple seconds to go through these, right? So we want to label the forces matched on the given acceleration, right? Based on a given acceleration. So remember that we know that the sum of the forces equal to mass times acceleration. So how they did it in the example up here, right? Let's say if this object has acceleration going to the right at 2 meters per second square, right? So how you could describe it is, and this is why they give you options, is this 1 kilogram object has 2 newtons pulling it to the right, and then 2 newtons pulling it back to the left. So that could be friction. This could be a pull. This could be a push, applied force. But when we look at it, right, when we take the sum of those forces, right? So if I was to sum of these 2 forces, right? Is really, let's say, 4 plus, and I put -2n. Why did I put -2n? Because they're going in opposite directions. So I'm adding the sum of the forces right here, right? So where now I have 4n minus, to just make it easier, 2n. So now the sum of my forces is equal to 2n. Now with me knowing that, right, I can take this back up here, 2n is 2 newtons. Up here and do my second law equation. So my force is equal to mass times acceleration, right? I know that this is equal to 2n. This is equal to 1 kilogram because it says so in the box, right? That's the mass of our object. And then now I have A, which is my acceleration. I see multiplication, so I do division. I divide by 1, divide by 1. Therefore, my acceleration would be equal to 2 meters per second. So that's how we checked it, right? Right here. So if we draw this diagram like this, then we could have the same acceleration here. And this is how we find it, right? So we kind of want to go through and do this backwards. So let's do the first one. We have 2 meters. Actually, let me clear all of this. Excuse me. So the first one we have is 2 meters down. Sorry. Acceleration is 3 meters per second squared and it's going down. So how would I want to start this one off? Let me try. Just a random force. Let's do, we're going down, so we got a force going here. And let's just do another force counteracting it, all right? So really, we need to figure out what does the sum of the forces need to be equal to. So let's do that one. I know we have an object with a mass of 1 kilogram. In the example, I did it backwards, right? But I'm gonna do it this way, right? And I know my acceleration is 3 meters per second squared. So now when I do that multiplication, I have a total sum of my forces of 3 newtons. So now that I know this, the sum of my forces must be 3 newtons. What combination of these two can I do to where I have a sum of my forces of 3 newtons? If I need also to my acceleration to be down. So if I need my acceleration to be down, which force should be bigger and which force should be smaller?
The down should be bigger.
Good. So now with knowing that, give me a combination of numbers to make this sum of the forces equal to 3.
1 and 2.
Now let's do that, okay? So let's, if I put 2 here, right here, and 1 here, right? When I add these together, right? Hold on. When I add these together, right? I got 2, and then I add 1, right? But what do I have to treat 1 as?
Zero.
Not 0, but look at this direction.
Oh, opposite, negative.
Negative, right? So now when I do this, right, I really get, that's a minus in front of the 1, right? 2n minus 1. Now what's the sum of my forces? Really become 1.
I was going to ask that. Aren't we supposed to be subtracting?
So you're adding, right? All the time. The sum is always adding, but adding, addition, and subtraction go together. But really, it becomes subtraction when you add the direction, because now we're adding a negative because it's the opposite direction. Well, really, we could change that now into subtraction. Does that make sense?
So if it's no negative, you don't subtract?
No, you just add. Because think about it. If it's no negative, like this example over here, they would just be in the same direction. Like this 1 and this 1, they in the same direction. So the sum of the forces would just be 1 plus 1.
I get what you're trying to say. You're trying to say that, you know, adding or subtracting a positive number is the same thing as adding a negative number.
Correct. And the best way to go about it to not confuse yourself is to kind of get away from the mathematical and think about the direction. The positive and negative really are not like, oh, really so much about the number. It's really more to give you the idea of the direction. So if you see a negative, think opposite direction. So then you would think that the two forces going in the opposite direction that would have like they would counteract, right? So if the one is bigger, then the one that's going to one is bigger but have the bigger effect. But say if they're going the opposite direction, they're the same size, then it would just be 0. If yes, that's what I'm saying to say. So if there's opposite direction but they're the same size, it'd be like 0. But think about the direction, the positive, negative as the direction. So now coming back to what you just said, you just gave me 2 going down and 1 going up. Because they're opposite directions, they end up counteracting. So then the 1 in the bottom is bigger, but we still have to subtract them. So now we have 2 minus 1. So now our total sum is 1, but we needed to get 3. So how can I change these numbers so that I can get my total sum to be 3?
You said, how can you get the numbers to do what?
How can I get my total sum to be 3?
Add 2 plus 1
Okay.
or multiply 1 times 3.
Would it be 4 down and 1 up or something?
All right, let's try that one. I think I like that one. If I just switch this, because we're real close. So 4. And I just switch these, right? This is now 4. This is now 4. It's the same concept. I just changed the value, right? Now what's 4 minus 1?
It's 3, so the answer is 4.
Now that's just one combination, right? Now we could do like how they had on the other side, something like this, right? To where it's the 1 in the middle, right? And you could just do, like you just said, 2 and 1, right? Just like how they have it over here. Now, what's the difference over here? These two forces are in the same direction. So now when I do the sum of my forces, I don't subtract. Because they're in the same direction, I can just add them together. Same direction. 2 newtons plus 1 newton. So where now the sum of my forces is equal to 3 newtons. So it's not just one answer that fits all. Like you could be creative with it, but the idea is to understand really about the directions of how you add in the forces together. All right. That's the first one. Let's do the same thing over here with the second one. So I already have 4 newtons over here on this side, right? And I have 1 kilogram. But we know we have an acceleration of 4 meters per second, and it's going to the left. So this is the sum. So let's start over here. Let's figure out what the sum of our forces has to be. So what's my mass for this problem?
It's 1.
So we got 1, right? And what's my acceleration?
Hold on. I'm trying to see if they put in the problem.
Right here.
It's 2.
The second one. Do you see my mouse when you doing this?
4.
4, sorry.
There we go. 4. All right. What's 1 times 4?
4.
So the sum of my forces is
4.
4, right?
Mhm.
Okay. So that means the sum of my forces is to be 4, and it has to be going to what direction?
To the right.
Over here.
Where?
Can
On
you
the
see that?
problem 2?
Yeah, can you see that?
So if the sum of your forces is 4, isn't it already going to the left? I meant to the right. So it wouldn't be the right, it's going to the left.
It needs to go to the left. They're telling us it has to go to the left. They do have 4 right here, but it's telling us there has to be, the sum of them has to be going to the left. Say it again.
Wait, I think I'm confused. So basically with this box, with these free diagrams, what we're trying to do here is something different than what we did before. We're just applying to what we did before to this new technique, which is take the mass times acceleration and get the sum of the forces, which is supposed to be the answer to the other problem. So if it's 4, that means whatever the other one is something that has to equal to 4.
No, we're just drawing the different, they give us a situation over here, right? This is what they want us to recreate. A situation to where this object has an acceleration of 4 meters per second squared and is going to the left. But this is what they started us off with. So this is what we start off with. We have an object. The object weighs 1 kilogram. Sorry, the object has a mass of 1 kilogram, and it already has an applied force pulling it to the right. So we have to create the situation and change it to where now it reflects this over here to the left. So what we just did,
At the end, we have to do what?
we have to change this to where it reflects this situation over to the left.
I don't understand.
So what we have to do is we have to add some forces over here so that it gets the same value that we have over here to the left.
Because I did the first two, and then for some strange reason, I'm sitting here on the third one. Like, I don't know what the heck to do.
No, we right here, right here.
Yeah, so we're on this one. That's what I'm saying. So now the first arrow is to the right, which is
Oh,
four.
that's why you're confused. I see why you're confused. Because they just told you that it's a 4 right here. Yes. Even though I just told you that the sum of the forces is 4, they put a 4 right here to start you off. So now that we have a 4, that's actually good. So now that we have a 4 right here, right? We know that the sum of the forces need to be 4. We already have one force here, and we know the acceleration is going to the left. If the sum of the forces is, if the acceleration is going to the left, which direction is the sum of the forces going to go?
Right.
If the sum of the forces is going, the
Oh.
acceleration is going to the left, where's the sum of the forces going to go?
Down.
If the sum of the forces is going to the left, where will the force? So if the acceleration is going to the left, the acceleration is in the direction of left.
Oh, applied force goes up.
Hold on, slow down. If the acceleration is going to the left, where will the force go?
To the left.
Yes. So now that we know that, right, we need to make sure this diagram shows that the sum of the forces is going in the left direction. But right now we have 4 newtons going in what direction? By the diagram over here to the right.
To the right.
So now I need to make sure that I have the sum of the forces be equal to 4 and going to the left. Right now, it's equal to 4 and going to the right. So we needed to not only change direction, we needed to be that 4 on the other side. Does that make sense?
Yeah, now that makes sense.
So now what do I need to add to this diagram so that I can have the sum of my forces being 4 over on this side?
I would say 8.
Exactly. There we go. Because now let me do this, right? Let me just say right is positive, right? So where now I'm going to draw 8 over here. If we just treat right as positive, then that means 8 has a different direction. So I have to do negative plus the 4 newtons that's on to the right. I'm just treating right positive because that's usually just how we go with it, right? So now when I add those, what's negative 8 plus 4? Or 4 minus 8?
4.
Positive or negative?
Negative.
Negative, right? So it's negative 4. What does that really mean? If right is positive, then negative 4 means I have 4 newtons going in which direction?
The opposite.
To the left.
To the left. Opposite. Yes, correct. So now we have what we need. We have 4 newtons going to the left. And then if we were to divide the 1 kilogram, we would have 4 meters per second squared as our acceleration. In which direction? The left. So now we got what we wanted.
Didn't say we have to add 2 forces. So would you just add like a normal force or something?
You could add either 2 forces here. You want to add 2 forces? All right, let's add 2 forces. Where do you want to add it?
Forces make a difference.
We want to make sure it doesn't. We want to actually make sure it's easy. So now we know we need to have basically more on this side. So let's just make it crazy, right? Let's say I want to add, I still have to get the 4. My sum of my forces still has to be 4 in total going to the left, right? Well, let's say we add a force on the right side just because, right? Let's add a force on the right side just because. Give me a number.
16.
So I'm going to add 16 on the right side. So now I have 16 newtons plus 4 newtons on this side. So on this side, I have 16 plus 4. What's my total forces on the right side?
20.
20, right? Now we know we have to get to a total of
4
4 to which direction?
to the left.
To the left. So if I have 20 on my right, what do I need to add to get to 4 on the left?
If you have 20, what do you need to add to get 4 on the left? 8.
Hold on, slow down. First, what direction do I have to have it in?
Left.
Left. So when I'm adding, what am I adding? Is it going to be positive or negative?
It's negative.
All right, so let's start with that. So we got our negative, right? So we need to have a negative number. Now, I want it to be, if I was to add 20, what would I get in total?
24.
Okay, you got the answer. Yes. But do you know how you got 24? Obviously, if you got the answer, you know how you got it. But can you repeat how you got 24?
It's 4.
4, right? Because if it was just negative 20 plus 20, then we would be at 0. But we just need to get a little bit more to get that 4. So let's add the negative 4. So that's why we do a negative 24 right here. So now when we add together, we have negative 4 newtons. And that negative is just a direction. So now we know we have 4 newtons going to the left. So let me write it like this. So now this is like the 12, the 2 that we just added. So now that's 2. And this is what I'm just showing you. It could be any combination. The real idea is just to understand how the vectors are working, right? All right. I feel like I did a lot of talking to like kind of put it together. So now I'm going to take my hands off the wheel and kind of just like, I want you guys to guide me for the last one, right?
Okay.
So we need to recreate this situation over here. So where now we have an object that has an acceleration of 2 meters per second going in the down direction. And we're starting off with 3 newtons going down and 2 newtons going to the right. So
Okay.
what forces would you add? Go ahead.
Well, can we write the thing first? Because it's easy to equals mass times. It's easier for me to see it.
Go ahead. Tell me what to write.
E equals mass time acceleration. I mean, the sum of all forces equals mass time acceleration.
And what else am I putting after that now? Next
So
line.
then I think this is a 2-step problem.
Okay.
So I would start with the 2 first.
Okay.
So I would do 2 times 2, negative 2.
Now, what's 2? Now, this is probably the best thing for me to say. You see it's 2 2's, right? It's this 2 for the acceleration and the 2 for the forces, newtons. Which 2 are you talking about and where are you telling me to put it at before I start writing?
I will put the first 2 where it's at because
What's the first 2? Which one? The one for the acceleration or the force?
box.
The one to the box?
No. It would be 1. I'm sorry. It would be because the mass is, so it would be 1 times 2. Sorry.
And what is that 2? That 2 is what?
Negative.
Okay. All right. I see where you're going. Because it's in what direction?
It's right.
Hold on. That's what I was about to say. All right. Are you looking at this 2 or this 2?
Yes. No, I'm looking at the first 2.
Now, what is that unit next to that 2? That letter.
Mass.
What's this letter next to this 2 right here?
Oh, yeah, I did it wrong. So I would do mass time acceleration. So I would still do a 2, but that's because I got lucky because it's only a 2. It's already a 2. So it'll be 1 times 2 because because acceleration is 2.
There you go. All right, cool. So now we got this 2, right? Now you said something earlier about it being negative, which I do appreciate you saying that because what is the direction?
The direction is right.
Hold on. Look at what they told us it was. This is what they told us.
I meant down.
Right? So this is like similar to kind of like gravity, right? So that we know like the sum of the forces must be equal to 2 times 1, which is how much?
2.
And this is in the down direction, right? So I'll even just add the negative so we know it's down. So we know we need to have a sum of the forces that's equal to -2 or 2 newtons in the down direction. Now, right now, that's what we have to have. what forces do we need to add to have the sum of the forces equal to -2 in the down direction?
What forces do we need to have? Applied force?
Okay, that's fine. But just how much? It doesn't really matter what the type force is, just how much the force, like the number for this one.
6. Maybe 6 isn't a good number. I would say 18,
Well, when you're saying the number, why'd you say 18?
because 2 and 3 have 18.
So now,
Close to 18. Wait, 15, 16. Yeah, I was right. 18.
so you want it to be -2, right? So why are we saying -2? Because we need it to be 2 in this direction going down.
Mhm.
Right now, how much do we have in the direction going down?
3.
3. And we need it to be, so let's say it's 3, also 2. You can treat it as -3 because it's going down. So right now we have -3, but we need it to be what?
2.
So if I need,
Oh, okay, 1. So it needs to be 1. Okay, so when you explain it, this one is kind of confusing because honestly, I was looking at the other one.
okay, so yeah, so
The
we got,
other 2.
you got it. You said 1, right? So now I'm gonna put a 1 right here, right?
Mhm.
So now if I take the sum of those, I should get 2, right?
Yeah.
Now, but also think too, do we have acceleration in the left and the right?
We still have it in the opposite direction. One's up, one's down.
But the acceleration is in what direction? Up, down, or left, right?
The acceleration is down.
And down, right? But do we have, by what they just told us over here, do we have acceleration in the left and the right?
No, they didn't say nothing about it.
So as this diagram is showing right now, we have an unbalanced force going to the right. An unbalanced force would cause an acceleration to go to the right, but they didn't tell us to have that. So we need to fix that to create a balanced force in the left and right, balanced force in the left and right. How would I create a balanced force in the left and right?
I don't know. I just know it's a 2-step equation. I don't know if we use
Hold
zero.
on, hold on, hold on, hold on, hold on. You don't gotta, it's not even that deep. If I got 2 newtons over to the right and I want to balance it,
You put the
what?
same thing on the left.
Exactly. Do you understand that?
Oh yeah, thanks whoever said that.
That's all we got to do. Because if we put this on the south now and the left and right, we balance. So now the only thing we have acceleration is in the down direction. Let's think about it. The forces are unbalanced in the up down vertical direction, but in left to right is balanced. Does that make sense?
Yeah.
Okay. Now let's see. I'll erase that, all of that real quick.
Thank you. That was easy.
Hold on. What just happened? All right. Okay.
We didn't get those answers.
No, this is fine. It's just you could have different rider answers. Now I will say for this last one, right? They did treat 2. They made sure they found like the normal force and the weight for like each one. Like I didn't ask for that, but it could be any combination. But what you see right here is a difference, right? So they added this 10 right here and then 11 up top, which is the same thing as you adding the 1 that you just did and leaving it leaving it here. They just added 10 because technically the weight of it would be 10, which is fine. But
Wow.
what I'm saying is this one right here, I still want you to treat it as they didn't tell us to have an acceleration to left and right. So that's why I made you do that last one where you made it add the force over to the left. Now that is also very important when we talk about forces in 2 dimensions, because you might have balanced forces in your left to right horizontal and have unbalanced forces in your vertical. So that means you have an acceleration. We see that a lot in projectile motion, where we see acceleration due to gravity in the up and down versus no acceleration in the left to right. That's why when you see something you travel and you throw something, it's going to keep going horizontally at a constant velocity, but you'll see it start to slow down and drop in its height as it goes through vertically. So that explains that. Now let's get into some more forces. Let's apply these forces to what we've seen before with resultant vectors, right? So these are all just different vectors that we've seen before. You can still see my screen, right?
Mhm.
Yes.
So now we want to identify the resultant vector, right? The resultant vector, remember? The vector that comes from adding the other 2 vectors. So like the answer of adding 2 vectors together. So what 2 vectors sorry, which vector is the solution or the solution of the other two vectors? Let's start with this first one right here.
C.
Let's see. So you say C, right? Let me draw C real quick. So if I do, all right, let's do it like that. You said C, right? So what would be the equation? How would I get it? C equals what?
C equals. That wouldn't make any sense. I'm sorry. The result would be A. It would be
Okay,
C plus B equals A.
there you go. So if I do C, oh, I was way off. That was crazy. If I do C plus B, I should get A, right?
Mhm.
So something like this, right? From my start to my finish, I get A from C plus B. Does that make sense?
Mhm.
Do we agree with that?
Yes.
All right. So C plus B equals A. We see equals A. I won't draw all of that. All right. Let's do the next one. What do you see?
A plus B equals C.
Let's do that one. So I'm going to do it in green again. We do A plus B. Are you supposed to get C? Let's see. Going from here to here. Does that look all right?
Mm,
To me,
I don't know. I don't know. It feels like those arrows, the arrow in that B and C corner.
No, it's right because it starts at A and ends at B.
Okay. All right.
A. If I travel it, right?
Okay.
And really, you could tell like this, right? If I travel from A and B, right? If I follow the path, is my displacement from my start to my finish, is it C? Let's look. So I go A, I go up, and from end to end, then I go to B, right?
Yes. It's C.
Where did I start to be? C. There we go. So C would be my resultant, and then my equation would be A plus B equals C. Is that what we got?
mhm.
All right, okay. Now that was just review, right? We went over that. That was all unit 3. We're almost there. We're still doing a little bit more review, right? Now, remember this when we started talking about vectors and the direction and the components
Yeah.
that go along with it? Yep. Okay. So now we want to determine the direction of the two components and indicate which component has the greatest magnitude. So remember we had our coordinate. Oh, that's why I'm like going crazy. I was supposed to clear it up.
Yeah, I remember it would be like the first one would be northwest, but I don't remember how to get the magnitude.
What was I about to say?
Oh, 180.
So we do, let me just draw it. So you started me off. We have our north, south, east, just like we in DC, right? Now I'm gonna go to where you know, like this is northwest, north, east, southeast, southwest, right? Now, if we go back to the math aspect that goes with this, this is quadrant 1, 2, 3, 4, and we represent them by the angles. We don't really need this for this problem, but I'll just make sure I go over it. By angle 90, 90, 180, 270, and then we back around here at 360. So this is 0 and 360 after we make one turn, right? So now, what we want to do now is figure out what are the two components and which one of the components have the greatest magnitude. So let's do the first one, right? What quadrant is that first vector in?
Northwest.
Northwest. So what two components would that consist of?
180.
Components. If it's northwest, and also look at the question. They have east, west, north, and south. If it's northwest, what two components is that?
West,
and
north and west.
there we go. Now, when it's saying the greatest magnitude, right? We were trying to figure out which component contributes the most to the vector. Now, looking at that, right? Is that vector more going towards the north or going more towards the west?
To the west.
To the west, right? It's closer to the W. It has even by the angle, right? So we would treat that as it has a higher horizontal component than it does a vertical component. And in this case, because it's northwest, we would say that the horizontal component is greater than the vertical component. So which component would be the greatest magnitude based off of that, just looking in northwest for this vector?
West.
Correct. So now for this one, we have north and west, and then the greatest magnitude would be west. Does that make sense?
Yep.
Let's do the next one. What is the magnitude, the components for this vector in the middle?
Southeast.
So we got southeast, so we got east in the south, and then which one is the greatest magnitude?
The south.
South, because it's closer to the south. The S. Good. Let's go to the next one.
Northeast.
Northeast. Good. So now we got northeast, right? We got east, and we got north. Now, which one will have the greatest magnitude?
The north.
The north. Good. Is that what we just had? Does that match up?
Mhm.
All right. Still getting to where it seems like it's a little bit of review, but let's put it all together, right? So the whole point of this is to be able to now identify individual components, but also let's be able to find them, right? So now what is doing this, right? We have two scenarios of given forces, right? We want to use trigonometric functions to be able to find what the actual value is for each one of those individual components. So now let's do that. Let's look at this first scenario, right? We have a 5 Newton force and it's exerted upon a dog chain, right? So like you got the dog that's like outside and he's chained to the fence or whatever, right? So that's a force to keep them there. It's a tension force, right? So we want to figure out what is that the individual components for that force, because you know it's going to be like at an angle. So how we do this, right? We're going to look at the problem, but we're going to have to represent it in that type of triangle format that we talked about earlier, right? So technically, it says the force exerted upon a dog chain at an angle of 65 degrees above the horizontal, sorry. When it says the horizontal, it means this part right here. So we create an angle between the chain and the horizontal part, and that angle is 65. So what I really want to do is, let me pull this out to where I can then make my vectors have this type of angle, right? Which we know is 65. So that's my vector, right? Now, with me knowing that, right, I can actually recreate this now as a triangle. So now I have 65. And then this is my force, right? My force is 5 newtons. But then my force has a y component
An X.
and an x component. Yep. Now, we can use the trigonometric functions to be able to find out what that actually is, the y and the x, right? So now I know my angle is here, right? I'm gonna look up here and I want to find, let's start with my y component. That is, my y component is opposite of this angle. So I would use sine. Sine of the angle is equal to opposite over the hypotenuse. So I can set it up now. Sine of, usually I would rewrite the equation. I'm just not doing it because it takes a lot with me doing with this pen thing. But I'll say it out loud. So sine of the angle is equal to opposite over adjacent, right? Opposite over hypotenuse. So I'll do the sine of 65 is equal to, I substitute in the y part component of my force. And then what's my hypotenuse? 5. So really what I would do is then 5 times the sine of 65 to cancel it out, and I get my Fy. So then my y component will be 5 times the sine of 65. Anybody know what that is? You have the calculator.
4.5.
Say it again.
4.5
4.5.
is the final answer.
Here we go. So now, how would I find out what my x component is?
The same way, but with cos.
Here we go. Yes, sorry. The same thing, but with cosine, right? So let's do cosine . 65 is equal to, dang, I'm tripping my fault. F of x over 5. So now with us doing that, we just multiply by 5 each time. So then we left with f of x is equal to 5 times cosine of 65. What is 5 times the cosine of 65? Somebody who has a calculator?
Then she said it was 4.5.
That was sine. We got to do cosine now.
2.1.
2.1. And the unit for both of these is newtons. So we got 2.1, 4.5. Now the answer, the number is not as important. It's more so being able to find that. Now the process is the same for the second one, right? So let me clear all of this. Now we have a baseball and it's being hit with a bat with a force of 325 newtons at a direction of 105 degrees. So really it's like this, right? And it's 105 degrees, which is greater than 90. What type of angle is that? Is that acute or obtuse?
Obtuse.
So it's obtuse angle. So now we know it's obtuse angle, so it's really going over that way. So now when we look at it, right, it really is here. And how I treat it is, if this whole thing is 105, right, then I'm looking at, this is what I'm about to do. Yes, I'm going to just do it this way. This angle right here, which would be, because this would be a supplementary angle, 180 minus 105. And what's 180 minus 105?
75.
75. My drawing's a little bad, but let me pull it out, right? So now I'm going to treat this as 75 over here, right? This is just me for doing visually. So now I know that this still is 325. And now I need to finish my triangle to where I can find my y and my x. So if I want to find my y, it's opposite of the angle. So I use what function?
Sine.
So I'll do sine of, for me, I'll do,
Will the answer be the same if you use the angle that they gave?
let's try it out and let's see.
Probably not.
So Lakshmi, you do 105 and I'll do 75 and we see if we get the same answer.
Okay.
325.
Is that for y?
Yes.
Um,
I'm plugging it in my calculator. I got 75 sine of 75 times 325 and I got about 313.9.
I got 314,
Oh, did you round it?
probably.
Yeah. Okay. So it's the same thing.
It's crazy how it's the same one, even though the numbers are different.
But think of okay. Let me finish it before I explain. I'll just round it, saying 314. Fine. Now we're gonna do cosine, right? Here's where you're gonna see a difference, right? Lakshmi, you do 105, and I'll do 75.
Okay.
All right, so then you do f of x. I'm gonna do 325 times cosine of 75. I got about 84.
Yeah, I got that too.
Now, did you get 84 or did you get?
I got negative 84, which I guess makes sense because it's in the like left side of the graph. Is that
Exactly. So when you
Okay.
say direction of 105, go back to our quadrants, right?
so? Like the magnitude is the same, but like okay.
Yes. That 105 is over here, literally over here. If we treat north and east as positive and west and south as negative, the vertical component is still the same to where it's still going to be in the north, right? But what we see where we're flipping it is we see it on the west side. So that negative represents that, oh, it's on the west instead of being positive from the east. So that's why, but
Okay.
why I said I wanted you to show is because the 105 captures that. It captures that it's an obtuse angle and it's going over to the west versus the 75 is the reference angle in that quadrant. So
Right.
for me to know this when I make my triangle, I have to keep in mind that I'm over in the second quadrant. So anything XY is really in the second quadrant really is negative. So that's how, let me erase this.
Can I ask a question whenever you're done?
Yes. When you think about your quadrants, right, you got to think about it as what's in each quadrant. So you got the first, second, third, fourth, right? This one is just like when we was in middle school. It's positive, positive. The X is positive and the Y is positive. This one, the X is negative and the Y is positive. This one, the X is negative and the Y is negative. This one, the X is positive and the Y is negative. And how does that relate? Northeast, northwest, southwest, southeast. Okay. Courtney, go ahead.
My question is do these coordinates apply to the Earth? Like, is that why sometimes it's like magnetic shifts and poles and stuff, and earthquakes and different things like that?
What was I about to say? This actually coordinate system does apply to like how the stuff like with compasses and works. And yes, like if you were to take physics 2, right, and you start doing this like teaches you the basics, just understanding like vectors, coordinate systems, all of that, because you actually start to care about like magnitude and like north, south, east, and west when you get into like physics 2 and start looking at magnetics, right? Looking at the North Pole, like the how things attract to each other and the direction of it. Like you actually do see all of that, and that's big with compasses. So yes, this is how the Earth works. Does that answer your question?
Yes, thank you.
No problem. Oh, let's check the answers. Typo, definitely a typo for that first one because there's no way it's the same answer. But that's usually what we got. We good?
Yeah, this one is just always a little bit more challenging than the other ones.
Because we start adding that math, right?
Exactly.
As long as you got the idea, I try to stay too far away from it to where it's like we just at least just like we touch over it, but like really just getting the idea of it. Now, where this one gonna come in handy, right? So now we talked about understanding those different components, right? But why do we need to know those components? We need to know those components so that we can analyze the equilibrium states for the problem that we're trying to do later on, right? And what does that mean? Analyze the equilibrium states. From unit 1, right? We talked about balanced forces. And I'm going to actually just read through the review, right? If the forces acting on an object are balanced, the object will maintain a state of motion. Do you remember what law that sounds like?
Newton's, if the object is at rest, it remains at rest. If an object is in motion, it only does so when acted upon by outside force.
It's in motion, it maintains state of motion, but it only accelerates or changes if it's acted upon an outside force. So yes. But which law is that? Do you remember? First, second, or third?
That's the second.
The acceleration one is second. But if an object maintains a state of motion, that's Newton's first law. So balanced forces relates to force first law. See you Monday. So now, when forces acting on an object are balanced, we call this state equilibrium. So if an object is in motion, stays in motion unless acted upon it by an unbalanced force. But when that object is balanced, the force on the object is balanced, we call that state equilibrium. When the forces are balanced, we say the net force is equal to 0. So if the net force is equal to 0, the state object is in the state of equilibrium. We can also say that too. Now, the purpose of this problem, right, is to figure out what statements are true when an object is at equilibrium, right? So this can help us put all together. We need to do this because it might be confusing, but if you can understand these verbal concepts of what it means to be in equilibrium, then the math will be much easier, right? So let's go individually by each statement, right? When an object is at equilibrium, right? Of an object at equilibrium, each one of these, right? If an object is at equilibrium, it's guaranteed that the object is at rest.
True.
You say true?
Yep.
Do we all agree on true?
False,
Why do you say false?
because it just could be in motion, but not
Not
Right.
what? Not what?
accelerate.
There we go.
Accelerating.
There we go. That's the big word. Because an object can be at rest or it can be doing what? What's the next one?
Continuum.
Or what are we talking about? Maintaining its what?
Equilibrium.
Hold on.
Speed.
What? Read it.
It's maintaining its state of motion.
Yes, maintaining a state of motion. So are we saying A is true or false?
I don't know because now I'm confused.
Hold on. Are we saying A is true or false?
I thought it was true,
I need to know.
but from what they say, it's false.
I need us to have a concise answer. I heard one true, one false. Someone break the tie. I just need one person to break the tie. Whatever you pick, I'll go with.
I'm gonna go with false.
All right, so we're going false for the first one. Now for the second one, the object is maintaining a state of motion, true or false? If it's at equilibrium.
True.
I got true. Anybody else differ or the same? Is that a agreeing for true?
I think it's true, yeah.
All right, we got another one for true. Okay, we got true. All right. This next one, right? So let's go. The object velocity is not changing. Is that true or false?
True.
Anybody else? For
Wait,
true?
wait, hold up. Now
Jamie,
don't beat
answer?
me up. Wait, don't beat me up because acceleration is just the direction. Velocity is the speed and direction.
Acceleration is also a what?
It's a scalar. It's a vector.
It's a vector, so it has magnitude and
Velocity.
velocity.
Object's velocity is not changing. I think it's false.
Hold on, real quick.
Or wait, true.
Go back. Acceleration is a vector, so it has magnitude and D word
Direction.
direction, right? So that's what we have to look at with acceleration. Now let's go back to this, right? Acceleration is the what is equal to the what in velocity?
Change.
In velocity over.
Time.
Time.
Okay, so now if an object's velocity is not,
Changing.
then is there an acceleration present?
No.
So if there's no acceleration present, then that means that the forces are.
At rest.
Balance. They're balanced.
Equilibrium.
So then if the forces are balanced, then we call this state.
Equilibrium.
So is this true or false?
It's true.
Anybody object? You see how like you got to kind of walk yourself into and talk into it? Let's do the next one. Are we at equilibrium? If we're at equilibrium, we can say that the net force on the object is equal to 0 newtons.
True.
Anybody object? Okay. If we are at equilibrium, we can say that the object is not accelerating.
Wait, because we just said acceleration is the change over time, the change in distance over time.
Changing.
Direction, sorry.
Changing.
Magnitude? The change of velocity over time.
Over time. So if it's the velocity is not changing, that also means the object is.
Not accelerating.
And we just said up there, you just said that the object's velocity is not changing. That's true. So that's also saying that it's not changing, that it's no.
Acceleration.
So if we're in equilibrium, then can we conclude that the object is not accelerating?
Yeah, so it's true.
Anybody object? Okay. Next one. The individual forces acting on the object are balanced. Can we conclude that is true in equilibrium?
I'll say false.
Anybody else?
It would be true, right? Like that's what we've been saying this whole time.
I need a debate.
Wait, let me read this again. The individual's forces acting on the object are balanced. Nothing should be acting on the object.
Hold on. Go back. Actually, look at the review.
I feel like I got to remember it in my head, which is an object stays in motion unless it's acted upon by outside force. So that
Okay.
means it's in equilibrium until it's acted on by outside force.
There you go. And what causes it to be equilibrium? What has to happen between the forces? The individual forces on the object must be.
Balance.
So therefore, if
it's
we're in
true.
equilibrium, okay. there you go.
Actually, was right. It's true.
Talk yourself into the answer. All right. All individual forces acting on the object are equal in magnitude. Is that true or false?
I don't know because I don't really understand magnitude.
Magnitude is the what? If you have a vector, right? It has a direction and it has a
This is displacement.
hold on, not displacement, direction and a
Magnitude is just the quantity.
so the N word. What is that?
Newtons.
Newton
Sorry, not Newtons, but what was I about to say? Number.
number, yeah.
So
Mhm.
magnitude is just the number. Which makes it a vector is you have a number plus a direction. Magnitude is a big word for number. So we're saying all the individual forces acting the object are equal in their number for it to be at equilibrium.
True.
You say true? Anybody else? No objections. We going false and everything else.
The
Basically,
first one I think is true still.
you still think it's true?
Mhm.
I think we lost the consensus on that one, so that's why I picked false. But let's see what the answers are. So basically, A and G are the ones that are false, but everything else is true. Now, anybody confused why B, C, D, E, or F is true and want me to go over those? Or are we good on those?
Oh, I'm good.
All right. Now let me focus on the A and G, right? So we're thinking about it, right? It's like those tongue twisters where it's like, this is true, but this is like this happens all the time, but this doesn't mean this happens, like those type of tongue twisters, right? So an object at rest is also equilibrium, right?
Right.
But just because an object is at equilibrium doesn't mean that it's at rest. Now, what does that mean? That means the object can be moving, like we said before, but it's moving with a constant velocity. If it's moving at a constant velocity, that means that its velocity is not changing over time, which means it's not accelerating. So it's going to keep moving at that pace until an outside force acts upon it. What does that look like? That looks like me pushing a car against a frictionless surface. So it's going to keep sliding and going, moving forward until an outside force stops it, right? But like, say that same car is going and moving, but it's on a friction surface, right? A friction present surface, right? It's going to eventually slow down, which is me decelerating, which is some type of acceleration, because it's going to have a force of friction acting upon its motion. And it's an unbalanced force. So just because an object is at rest, it is at equilibrium, but just because if an object's at equilibrium does not mean it's at rest. It could be moving and just maintaining a state of motion. Does that make sense?
Yeah, that makes sense.
All right, let's go to the last one, right? So it's saying all individual forces acting on the object are equal in magnitude. Equal in magnitude means that it's something like this, right?
Oh, it has to be balanced, not just equal. Ugh. Okay.
This means equal in magnitude, right?
Balance doesn't always mean or equal doesn't always mean balanced.
Do these individual forces all have the same magnitude?
Yeah.
No. Oh wait, is that a 2 up top?
That is a 2.
Oh, my bad. It's yeah, they do.
Is this balanced?
No.
This is not balanced because I don't see a bottom force.
Exactly. Now, that doesn't mean what I showed earlier was 2 balanced forces with equal magnitude. But now I have all equal magnitude forces, but they're not balanced. So this is one of those tongue twisters again. Does that make sense?
That makes sense.
Yes.
Yeah,
All
that
right.
makes sense.
We're doing good. This is very much tedious, but this part is very important. This will make the math part very easy. All right, let's do this again, right? One more time. Hold on real quick. Let me stop sharing. Hold on. Give me like 2 seconds. All right, let's go through this one more time, but now we want to look at in the following statements, right? In which case can you conclude that the object is at equilibrium? So now it's kind of like the tongue twister again, right? Now, if I see these situations, can I conclude that my object is at equilibrium? So if an object is at rest, can I conclude that it's at equilibrium?
What? I'm sorry, could you say that again?
I probably confused you, yes. But if an object is at rest, can I also say that it's at equilibrium?
No.
Anyone else? Did we say yes, true, false?
Oh, no, I'm sorry. For objects at rest, you can definitely say it's equilibrium.
Okay. Anybody else object? Or we all saying we agree?
I think it's true.
All right. I'll take your think as a true. Okay, that's disappearing ink. I did not want that. Hold on real quick. All right. An object that has constant, go ahead.
Sorry, I have a question. Is the so for the last one, if the object at rest that was false for why for like the last slide that we did, why would it be true now? Could you conclude that the object, if the object is at equilibrium?
Remember I said the tongue twister, right? Which of the following statements is always true of an object at equilibrium? So
Okay, yeah, I see.
that's what I'm saying. Is this like a tongue twister, right? But you got to be that specific because it's like just because an object is at equilibrium doesn't always mean that it's at rest. But now if we come to here, an object is at rest doesn't mean that it's at equilibrium. That's what I'm asking. Does that make sense?
Yeah.
So now that we know that the object is at rest, we can also conclude that it's at equilibrium too. Let's do the next one too. The object has a constant velocity. Can we conclude that the object is at equilibrium?
Yes.
Any objections?
Could you say it again?
We know that the object has a constant velocity. Is the object also at a state of equilibrium?
No.
Yes.
Hold on.
If it has a constant velocity, it's acceleration. It's not accelerating, meaning its forces would be in equilibrium.
Yeah, Sean is right, but Sean said.
Okay. So we saying true?
Mm-hmm.
Okay. Now, the object is moving. If the object is moving, can we conclude that it's at equilibrium?
No.
False.
Any objections?
Nope.
False. Now, the object has a constant speed. Can we conclude that it's at equilibrium?
Yes.
Any
If an
objections?
object is at constant speed, can we conclude that it's at an equilibrium?
That's what I'm asking.
No.
I got a no and I got a yes. Someone break
Yeah,
it
I'm going with Lakshmi and say no because wait, if an object is at a constant speed, can we wait? What?
If an object has a constant speed, it would also have. Wait, no.
Wouldn't it have equilibrium?
It would have acceleration. It would be false.
Oh,
Yeah, sure. That's what
I
y'all
think
doing.
I think it's false.
Wouldn't it be? What doesn't wouldn't velocity be acceleration and then speed is like, for example, like if an object is at a constant speed, like if an object is going like 60 miles per hour constantly, that's one thing. But if it has a constant velocity, or like 60 miles, right, constant speed, and then if it has a constant velocity of like 60 miles per hour, that constant velocity, wouldn't that technically like be able to accelerate and go up, whereas like the speed is just like it stays like at 60 miles? Or am I switching them?
What's the difference between speed and velocity? Maybe that'll help y'all out. It's one is a what and one is a the other thing is what?
Yeah, one is right, speed is scalar, right, and velocity is a vector,
Mm-hmm.
right? So wouldn't technically the constant velocity be false and then constant speed be true?
I think the constant speed is false because in the constant velocity, your acceleration does not change, but in the constant speed, your acceleration can change. You can like accelerate backwards. You can make a U-turn.
That's what y'all going with. Are you sure?
I
Right.
think it's false.
Thing about direction, so it's very like sneaky, but it's false.
We're going with false. I'm hearing false, so I'm gonna just leave that one as false. We'll come back to it. The object is stationary. If the object is stationary, can we conclude it's at equilibrium?
Yes.
Any objections? Not
Nope.
hearing any. Okay. The acceleration of an object is 0 meters per second per second. Is the object is at equilibrium?
Yep.
Any objections? Okay. The individual forces acting on the object are balanced. Is the object at equilibrium?
Not necessarily. Right? Is that what we were talking about? We were talking about
Tell
just
me.
because
No, the other one was equal. Here it says balance.
balanced. Okay.
So
It was
isn't.
equal.
Yeah.
Um,
the other one said
Okay,
equal.
then yes, balanced would be equilibrium.
Yep.
I think
Any
that's true.
objections?
G is true.
All right, let's see how we did. A, B, E, F, G. Okay,
We got them right.
we got them right.
You didn't mention C.
Those are the ones that are false. C and D. You mentioned the ones that were true.
Thank you.
Okay, now let's get into that D. The object has constant speed. Why is that one false?
Did I say it correctly? How you can like, make a U-turn and technically like change your acceleration?
You know, it's funny. The first time you said that, I was like, wait, what? But now I know what you're talking about. Because if you have constant speed, right? Name a thing where you have constant speed, but you don't have constant velocity. Name a situation where you have
Cruise control.
constant velocity.
Cruise control.
Think about
Right.
it. Constant speed, but not constant velocity.
A boat?
There's only one situation, right?
You tell me. What's that situation?
Floating in the moon.
You kind of described it earlier, Sean, just now.
Making a turn,
Making a turn, because what are you doing?
changing your direction.
So now if you're changing direction, does that mean you're changing the velocity?
It is.
Remember we talked about a car, right? The 3 ways you can change you can accelerate with a car, right? Is literally either going faster, slower,
Slower.
or making a turn. You got the gas, you got the pedal, or you have the steering wheel. Because if you think about it, right? You're accelerating when you're going in a circle because your direction is constantly changing.
Changing.
I say constantly changing.
Yay, I got it right. The U-turn was correct. I was trying to like make the connection.
So just because an object has constant speed doesn't mean that it's not changing its velocity. Just
Because
because
you can keep turning at 20 miles per hour. That's still constant,
constant speed, but not constant velocity.
velocity.
Does that part make sense before I move on? I'll take that as a yes. And then the object just moving, like just because it's moving, it could be moving and still be either accelerating or it doesn't have to. It could be at equilibrium. You don't know. You needed more information for that. But I did good. I did good. All right.
So it's already 8:30. Are we doing something new tonight?
That's crazy. I got 6 minutes. You trying to
How
get
much more do we got?
oh my goodness. Like what I got to do, man. I thought we was here to learn physics.
I'm learning.
No. This is the last problem. I want to do this one only tonight because I feel like this is a good conceptual one to help lead for the next time when we come back on Monday. And we could stop right here. I wanted to add this one. I got like 5 minutes. I don't think this will take too long. Because this is more thinking. Like this is not math. So we want to just fill in the blanks, right? With less than, greater than, or equal to. And what does that mean? We want to compare the different forces, right? and we want to see how they compare to each other by just looking at it visually. Remember how I said we have the free body diagram and we have the arrows, and like
Mhm.
if it's bigger in magnitude, then you write the arrow bigger. If it's smaller in magnitude, you write a smaller arrow.
Yes.
We want to compare the different components, right? So let's look. Let's look at the force 1 is X component, which is over here, and force 2 is X component. Now, what do you see about them?
They look to be about the same. If I'm correct, they would be equal to.
Okay, I'll take that. So
I
you want to say
feel
that?
like isn't the left one a little bit longer? But I don't know. It's hard to say.
I won't say
It's very hard to say.
That's what I'm gonna say. I'm gonna just say. What do y'all want to say? Do y'all want to say it's equal to, or you want to say it's a little bit longer?
I don't know. It could go either way.
What's the other words?
Can you say, do it again? I say, looks like it might be a little bit longer.
So you want to say it's a little bit longer?
Mm-hmm.
Okay, let's just go with that. Let's just say that F1 is a little bit longer.
Just
a little bit.
They're equal.
What'd you say?
I think it's equal. But let's go with greater than.
Let's go with greater than. I'm not gonna be too pressed, but I see where you're going from. But if they were the same length, would you say it was equal or greater than?
I would say it was equal.
Okay. I know the visual's a little off. Let's go to the right, right? Let's go here. Let's do the Y component. This one should be easier. The Y component for F2, this force over here, right? And we compare it with F3. Which one is bigger? Which one is smaller, or are they equal?
Wait, F2Y or F3?
F2Y and F3, we compare
Okay.
these two.
Oh well, the
F3
F3
is-
is way bigger.
Yeah, F3 is longer.
Okay, so we do greater than or less than?
It'd be less than.
Less than.
Oh
right?
wait, yeah, less than.
There we go.
F2Y is less than F3.
Now let's go with over here, right? Compare F1Y with F3.
F3 still looks to be the bigger one.
So greater than, less than, or equal to.
Less than.
Now let's think about it, right? If I was to take the sum of F1Y and F2Y and add them together, would they be greater than, equal to, or less than F3?
I'm gonna go with equal to because you're probably doing some weird geometry wizardry.
Weird geometry is hilarious.
I'm
else?
gonna go with equal because you're doing some weird geometry, I feel like.
Weird geometry. Anybody else say equal to or object?
I was gonna go with him, but I didn't think that deep into it. They just look like they could, if they stack on top of one another, it would be the same.
That's a good way to think about it. So I actually stop right there and we'll go from there because that's really what the purpose of this. What they say. Okay, so yes, for the first one, it was equal. Yeah, I was right. So I'll change that one real quick. But that one, I wasn't too pressed because, to be honest with you, I messed this all the way up because of how it's drawn. But let's just change that one to equal to. And then I remember that y'all put this one was less than, and this was equal to. So now let's look at all of them. I'll give you that first one to where we pretty much got them all right, right? But what was the purpose of this? It was to now get you to see what we're looking for in an equilibrium state, right? When we're looking at an equilibrium state, right, we're trying to see how we can get the individual components to match up on both sides, right? So if we separate everything here by this line in the vertical, right, how do we get the forces on this side to equal the forces on this side? So we want to make sure these individual forces together add together to equal this. Now, this is a special scenario because think about it, right? In what scenario would you want your forces vertically to equal your forces on the ground for like some real world application, right?
If I'm jumping out of a plane.
Wait, what? Oh, wait.
Right?
Wait, you want your forces vertically to be the same as your forces down?
Wait, if you're jumping out of a plane, aren't you going to get? No, you're right. Sorry, I wasn't
That's
thinking.
what I'm saying. I'm thinking, what would you want?
I want clarification. What was that question? What's happening?
When would I want my forces balanced equal in the vertical? Like
In the vertical and the in the
this vertical.
down. Yeah. Okay. When
The
do you
ship?
want that? When you're floating, when you're buoyant.
Okay, buoyant.
When
Or
you're
I-
at rest.
Huh?
When you're at rest.
Okay, you're at rest. I'll give you a very simple example, right?
So that's what I was thinking. When you jump out of a plane, you want before you hit the parachute, you want everything to be equal.
That is actually a good example. Yes, yes. But I'll do a simpler example, which will get to us talking about our problem. Hope we can get to on Monday. Who has paintings in their house?
I don't have none on my walls.
Or a picture, right? Like in a
Yeah.
frame. Think about it. When you have a picture in a frame or a painting, right? You have to do what with it to put it on the wall?
Use that little instrument that got the liquid in it with the bubbles.
I don't know what you're talking about.
level.
There's like a leveler.
The
Leveler.
leveler. Okay, the leveler. Okay. But
I don't
using-
know what it was called.
So you're using the leveler to do what though? Because you're trying to do what with the picture or the frame? Or
You're trying to balance it.
on what? You're doing
The
what
wall.
on the wall. So you have to do what with it on the wall? You have to
Nail it.
nail it so it can do what from the wall or from the
Pivot.
hang. Thank you. Hang. Well, you're trying to hang something.
So that's tension.
Tension because what? What's going against the tension that's pulling it down?
Gravity.
String.
Or
The
the
force due
the
to-
nail.
The force due to gravity from the object's
Wait.
weight. That's a simple equilibrium state, and that's going to be the problem that we are covering for this unit. That makes sense?
Nailing a paint into the wall.
You're going to literally see that next class.
Okay. All right. I mean, I get it. You have the nail has to be strong enough. I mean, are we gonna calculate all that though? Like,
Yes.
what if the nails? What if the weight of the painting is too much and the nail starts slipping? Like, are we gonna?
Yeah,
have to-
like that hanger thing, the string thing that's on the back. I get what he's saying. If let's say the nail is strong enough, but the string thing, sometimes it used to be like a metal one, and it used to break if it was too.
heavy.
Mm-hmm.
Yes, that's exactly. See, we were perfect. That's what we're going to stop right there because all this is exactly what we're going to be at for next class. Yeah, I got it.
We're about to calculate the tension of a string or a nail or something. Please
Yes,
don't tell me.
that's
Oh
exactly-
my God, that's stupid.
That's good. We're going to start off next class exactly with that problem. But hold on, let me stop the recording.